Energy. Does anyone want to define the word energy for us before we go any further? Because if we're in physics, how do we define energy? The capacity to do work? Like, is that what we're talking about when we're talking about energy here? No. Usually we're talking about something that is going to provide electrical power for our homes when we're talking, or for our cars when we're talking about energy. So in our context, energy is going to be almost always related to providing an electrical source for us. So why should you care about energy efficiency and renewable energy? Because at some point in time, if you were like, I really think I'm going to put solar panels on my house, somebody's going to ask you, why? That's kind of ridiculous. You can just buy your energy from the energy companies. Why would you want to do that? You might want to have some answers. And when we look at energy, everything runs on energy. All living things run on energy. And what is the ultimate source of energy to Earth? Solar. Solar energy causes winds, which move water. So solar is the ultimate source of solar energy, of wind energy, of hydropower, of tidal energy. Tidal, you could probably say the moon plays a role in that too, but the sun's important. Sun is also our ultimate source of energy for anything that's a fossil fuel, because that's what originally gave us the plant matter and then fed the animal matter that would have decayed, and the plant matter that would have been preserved, and things that created some of our fossil fuels. So solar is our ultimate source of energy. The energy that keeps your body and all other living things going is different than the energy that runs your car, your house, factories, lights, appliances. So we are talking about different types of energies. But both types of energy have the same concept of wasted energy. What do we usually call wasted energy? At least in physics, what would you call it? Entropy or disorder. So energy that is lost is usually lost as heat. Well, yeah, it's lost as heat. And it doesn't contribute anything. Let's see. Does anyone? Oh, well, Andrew plays soccer. When you run, you're using energy to create motion. Kinetic energy, movement of energy. But what is the byproduct of running around a lot? Heat. So you sweat to get rid of the heat. That heat is energy that is lost. You can't use that for movement, unfortunately. If you could, think about how much faster we would all be when we ran if we could also use that energy to propel us forward. Not quite an option. Same thing is going to be true of other uses of energy. We're going to have loss as heat. Who's anyone in genetics right now? No. Some of you have been in genetics before. What do we use to keep your fly babies warm?
Lamps.
We use lamps to keep the fly babies warm. Why? Because the lamps, the heated light bulb, gives off energy, which it does create light, but it also creates heat that we use to keep the flies warm, because our normal light bulbs give off wasted energy as heat. But wasted energy truly is a loss of money from that perspective, a loss of resources, but really both. Because does your car convert all of the money that you spend on gasoline into moving your car forward? Oh, if only it did. Think about how little money you would spend on gas then, and everyone would be really happy. Yesterday, I drove by a gas station on the way home, and gas was like almost $3 a gallon. I was like, when did that happen? Why is it above $2.80 again? Like, it wasn't last week when I filled up. This is bad. But maybe it was like Super Bowl Sunday gas prices. Maybe they were worse. And energy use does have an environmental impact, we're going to find. So a waste of resources is a big problem, Because if we're not being able to utilize our resources to the best of our ability, then we're always going to need more and more and more, and that's going to increase our ecological footprint. The flip side of that is the pollution that comes along with energy use is also problematic. And for the purpose of that today, we're going to skip the carbon dioxide pollution, and instead we're going to talk about sulfur oxide pollution and nitrogen oxide pollution. The SOx, S-O with a little x, subscript x, and NOx, N-O with a subscript x. Because you can have NO gas, NO2, SO2, SO3, SO4, so we can have different types of those gases. What happens when NOx and SOx gets into the atmosphere? Acid rain. Is acid rain a problem? If you live in the Adirondacks, it is a huge problem. They're having trees where they are losing leaves and trees are dying because of acid. We're finding that in the Finger Lakes, you're discovering that the concentration of aluminum and mercury in the water is very high compared to what it used to be, because as the acid gets into the soils there, it leaches out the heavy metals and brings them into the water column. It's changing the distribution of fish. It's increasing the likelihood of things dying from fungal infections, and it's a huge problem. Lancaster County, it causes a different problem. Sinkholes. Lancaster County is underlain by limestone. Lots and lots of acid rain over a long period of time makes that limestone weaken and can make areas more prone to sinkholes. So wouldn't it be great if we produced less pollution so that we didn't have acid rain problems? So renewable energy allows us to waste less money. It allows us to pollute less. It allows it to waste less resources. And maybe in the long run, it'll actually allow you to make money. That seemed like a crazy idea. In a lot of areas, not all, but in a lot of areas, and it seems to be growing, in order to get people to switch over to solar, as a benefit, one of the things they allow you to do is sell your excess energy that your solar cells collect back to your electrical company. Because solar cells can't provide you with all of the energy you need, so you usually have a connection to a backup to your electric company nearby. And if you're creating more energy at a time than you need, you can sell it back to the company. Not for very much, not for nearly as much as you would pay to get your own electric back when you need it from them, but it does allow people to make a little bit of money, and it allows the electrical companies to continue to profit. So, we did a little bit about our different types of energy. Renewable energy resources are ones that are replenished in some time of a short time period. For our purposes, we usually think of a shorter time period as something like your lifetime or smaller, or 100 years or smaller. This includes solar, wind. And if we're using a time period like that, it can include firewood from trees, because that is long enough for a tree to generally regrow, provided you're replanting a tree for every tree you take down. So trees, it's a little bit messy. Sometimes biomass is not as renewable if we're not replenishing it. Water and geothermal also can count as renewable energy. Now, there is a debate whether or not geothermal is really renewable, because geothermal energy is the heat energy given off from the earth. So the earth is giving it off as it goes through processes in the core and in the mantle of heat loss from the center of the earth out. So the earth isn't really reharnessing that heat to make it into anything else. It's just a byproduct of earth processes. But from the perspective of non-renewable versus renewable, geothermal does fall into that renewable energy category, even though it may not be. And then our non-renewable are things that cannot be replenished on a short time cycle. Oil, coal, natural gas, your fossil fuels. Could those be replenished on a long period of time? Absolutely. You know, millions of years of time, sure. Uranium, how about that one? Can that be replenished? Maybe not. But maybe it's not as bad as you think. Let's see. Generally speaking, non-renewable accounts for kind of like on average about 87% of the energy that we use. Unrenewable is about 13%. And this is dealing with the world's commercial energy. In the US, non-renewable makes up about 90% of our energy use. We find that air pollution associated with non-renewable energy kills about 1 million people a year. Having said that, you'll soon see that renewable energy can also create air pollution that can kill people. So that's not just a non-renewable energy issue. That is also just an energy use issue. But the CO2, the NOx and the SOx gases that come from non-renewable energy combustion are leading to environmental problems. This is showing us the world usage of energy versus the United States usage of energy. What differences do you see? Other than the 87 versus the 92. So we use more oil, don't we? Is anyone surprised that we use less coal than the rest of the world on average? A lot of that has to do with China. China has a massive usage of coal. But in the US, we often hear, especially right now, about if we go to more renewable energy sources, it will hurt the coal industry, which employs so many people in the United States. It does employ people, but that may also be a little bit overblown as we talk about how many people it employs comparatively to how much of it we use. Natural gas, we use a little bit more. Which we use less of? Biomass. It's true. Do any of you have a wood-burning fireplace? Couple. So then you use biomass sometimes to heat your house. Do any of you burn human feces in your? No? No one burns human feces to make energy? How many of you are really disgusted by that concept? You're like, that is not sanitary, and how in the world would you not get food poisoning if you cooked over it? Yeah, it's kind of weird, isn't it? It's a concept. We also use way more nuclear power. Interestingly enough, we use more hydropower. The United States is when it comes to hydropower, one of the luckiest countries in that we have the right infrastructure and the right amount of water and stream mileage and different relief, meaning elevational relief, to have good hydropower in some areas. Hydropower, the main drawback is that it can't be used in a lot of places. So that's why it isn't used more. But before we talk about the different energy concepts, different types of energy, it's important that we look at a little bit more of the concepts about energy usage. And one of the ways that we look about this is the concept of net energy yield. So how much energy do I get out of something? What's the second law of thermodynamics say? Okay, let's back up. What's the first law of thermodynamics say? Energy can't be created or destroyed. So the second law tells us that
in an isolated system, energy will naturally increase.
So we can change energy from one form to another, but as we do, energy will be lost through entropy. And disorder increases. So first law says we can't create or destroy energy. The second law says we can change it from one form to another, but every time we do, we're going to lose some. Okay. How many of you have ever cooked anything, including a s'more, over a campfire? Everybody. Good. Does the campfire cook food? Absolutely. Does it also give off a lot of heat that does nothing when it comes to accomplishing the cooking of a s'more or real food? Yes, it does. So that is energy that is lost. So it was changed from stored energy in wood to energy of heat and thermal energy, but there was some lost. We weren't able to use it all. And sometimes, well, anytime really, you're going to discover at the end, once you burn that, there's going to be ash left. So not everything was able to be transformed even from stored energy to thermal energy. There's always some energy lost. Net energy is the total amount of high quality energy that's available from an energy resource minus the amount of energy you put in to get it out. So net energy is our total amount of high quality energy available minus the amount of energy it took to get to that energy. If I want to build a campfire, the net energy is going to be the energy I get out of the campfire minus what it took to find the wood, build the campfire, use the match, create the match, all of those sorts of things. So net energy of oil is also going to include the energy we get out of the oil minus the energy it took to extract it and refine it in the first place. Wind power is often seen as a type of energy that we should all be able to transition easily to. But wind power at the beginning is really expensive because you can't just harness wind. You need to have something to harness wind with. You need to have some sort of a windmill. So to make the windmill, you need steel. Well, to get steel, you're going to burn the coal in order to smelt your metals to get your high quality steel. Then you're going to need to run electrical power and things for lights and equipment to take the steel and make a turbine. Then you're going to burn diesel as you take the turbine to the site in order to get it there. And then you're going to use more energy to put it all together. So you've already lost energy at the beginning. So net energy you get at the end after all of that. Energy is always lost. It can't all be recovered. And using energy does require energy. We lose a lot of high quality heat or high quality energy as heat. We will look at the net energy yield of things as we go through. And this is looking at net energy yields and different types of things that we can do and different types of use of heat that we can have. So coal has a high net energy yield. Tar sands have a low net energy yield. How many of you have heard of tar sands before? A few of you. We'll get there. It is not a good, you can see already it's not a good choice because it's a net energy yield of low energy, but it's also environmentally a really problematic way of collecting fossil fuels. Passive solar has a medium net energy yield, whereas active solar can be low to medium. What has our highest net energy yield does it seem to be across the board?
Reducing energy.
Reducing energy waste. Does that seem ridiculous to you? We lose a lot of energy though. One of the things that some companies are looking at is how can we harness the heat from the work that we're doing in order to heat our buildings? Or to heat the pipes, so you don't have to heat water pipes. So energy conservation and energy efficiency are going to allow us to harness that lost energy. Energy conservation is going to require us to improve our energy efficiency. If I can get more energy out of the same unit, then it's better because I'm getting a higher net energy, a higher yield. You want to increase the amount of work you can do from a single unit of energy. More benefits, less waste, same environmental impact. If we can reduce our resource use, though overall, by increasing our energy conservation, we can reduce our environmental impact. We're either reducing our energy use or our energy waste, though, in order to do this. So that's our two ways that we can reduce our resource use. Reduce waste or actually reduce use. What do you all know about an incandescent light bulb? Sure, normal light bulb that looks like that. This is the standard light bulb we've had for a really long time.
It lets out a lot of energy through heat.
How much energy do you think a regular incandescent light bulb wastes as heat energy? 40, you said?
30.
30, okay. Let's throw out some more numbers.
60.
It's 60.
45.
45. Let's throw out some wild numbers here, people. 90 to 95% of the energy from regular incandescent light bulb is lost as heat energy. Does that seem problematic to anyone? So the switch to fluorescent bulbs and LEDs is actually about saving energy, but beyond that, it's about saving money. Because if I am wasting about 16% of our energy, commercial energy in the US, is used to do work. About 84% is wasted. Ouch. Think about that if you ran a business and that was your budget. That's a problem. Because most of the energy that we use is low quality and a lot of heat is produced. This is a big problem. Much like right now, the machinery in the background is a really big problem. And if you're with me this morning, I was complaining about the smell. Price of fossil fuels in the US absolutely does not reflect the true cost of fossil fuels. If you look, fossil fuel prices in Europe, especially gasoline, are much, much higher than they are here. That is because it does include more of the factors. In the United States, government subsidies and tax breaks allow fossil fuels to cost less than they otherwise should. Also, like everything else, there's hidden costs involved. There's the environmental costs. There's also the health costs. 1 million people die a year from air pollution due to non-renewable energy. That's too many people dying from air pollution. Cars and gasoline, they say that studies have been done where if we try to forecast what would be their actual cost, including hidden costs, it would be $12 a gallon. Any of you want to pay $12 a gallon for gasoline? Because I do not. Of the energy that is wasted, 41% of that energy, 41% of the 84, so 16% is used for work, 41% is used to get that energy. So of that 84% that is wasted, 41% of it is for doing the work. The other 43% is actual net loss. This is not energy that we lost in creating the energy or transitioning the energy. It is energy that is just not usable through our current processes. Now we're going to look at our fuels. So fossil fuels come from ancient plants. Plants that died hundreds of millions of years ago. 81% of the world and 83% of the US uses this fossil fuel energy. It's considered non-renewable because it's not renewable on a human time scale. And when you use it, this energy is gone. When I burn a gallon of gasoline, that gasoline is gone. There's no way for me to reuse it. We have a little problem here. We have always used the easiest to find deposits of fossil fuels first. Those are the cheapest to obtain. which means we've gone through our fossil fuels that were easy to get to, or we soon will. So our reliance on fossil fuels is going to make things more expensive as we continue forward because it's going to cost more and more to get to the fossil fuels. And the cost of fossil fuels is going to increase as we deplete the supplies because there's going to be less of it and it's going to be more expensive to get to. Because let's think for a moment. If I'm going to own a coal mine, do I want to get to the coal that's 10 feet under the ground, or do I want to get to the coal that's 10 miles under the ground? 10 feet, right? It's cheap and easy. That 10 miles, it's going to cost a lot more. So I'm not going to go for that deposit yet. And that's kind of how we've done the business of fossil fuel extraction. We get the easy to get stuff first, which just makes sense from a business perspective. And in case you don't like thinking from a business perspective, well, for these chapters, that's a shame because that's how we handle energy policies here. I want to tell you we handle it from an environmental perspective, but I'm wrong. Everything's about a cost-benefit analysis when it comes to this because we're doing what is best, and a lot of it has to do with lobbying. Do you know that your congresspeople have to have science advisors on their staff? Doesn't mean they have to have a science degree, but they have to have a science advisor, someone who reads the science policies for them and tells them about things. It matters. In case you're ever looking for like a really interesting job as a way to get involved in changing policies, being a science advisor for a member of Congress would be great. They need people who can actually understand the science. Because how many of you have ever tried to explain like something minor scientific to your friends? And they're like, oh, wow, yeah, that I guess that makes sense. Like how vaccines work or something. I don't know, that one seems minor to me. The big one right now is, some of you know this, I don't know if my mom had cancer a few years ago. I get really angry every time I see people post these things about cancer cells can't live in an alkaline environment. Just make your body alkaline. It's true that cancer cells in the lab, when exposed to alkaline conditions, died. So would everything else. Your body cannot be made alkaline. Your body buffers its own system. So this idea that all you have to do is like drink these 3 things and it makes your body alkaline is false because it doesn't work. It works in the lab on a plate of like random cells on media, but it doesn't work in your body. And I have a friend who keeps saying like, your mom should have done this and this would have cured her cancer and she wouldn't have needed chemo. They're not really a friend anymore, but they're a friend of the family, so I can't, in fact, tell them what I would like to tell them and stop sending me the articles. But imagine that you are just like a random person and you see this thing and you're like, that is what we do. That's unfortunately how we've handled a lot of our energy policy and a lot of our environmental policies. Somebody comes up and goes, this is right. Raise your hand if you saw the story about the onion is the way to not get flu article yet. It's the new thing that's trending with Snopes. People are sharing on Facebook and Twitter that if you cut an onion in half and you leave it next to your bed, you won't get the flu because the onion is a sponge for sucking up bacteria. Did anyone else see that recently? It's not true. But I have people sending it to me this weekend because I'm a scientist and I would know whether or not it is true. It is not true. If you didn't like the onion one, there's one about garlic too.
Well, that's true. That keeps away the vampires.
Vampires, but not the flu. Now we're going to switch to some more renewable energy sources. You might know this about some of these things. You might not know all of this. So direct solar energy is a renewable, abundant source of energy as long as the sun exists. I need to throw that one on there because Dr. Bradstreet might say that this only works renewable as long as the sun is here, right? And he's right. This only works if the sun is here. You can use solar energy to cook food. Anyone ever cracked an egg just to see what would happen in the summer to see if it would cook on your sidewalk? Last year, my cousin baked chocolate chip cookies in his car in Arizona. He left them on a piece of aluminum foil on his front seat while he was at work one day. and came out, and he didn't eat the cookies, but they were solid cookies because he was afraid of food poisoning. But he cooked cookies in his car. You can, and sometimes, cook an egg on the sidewalk. Not saying you should, but you can. We also use heat to sterilize water. Boil water sterilizes. Solar energy can also sterilize water. Passive solar heating is something that humans have used as long as humans have had structures to live in. But it is well documented in the Greeks. The Greeks would build their homes and they would face them towards the south because that would allow them to capture the most sunlight. Passive solar systems allow you to capture heat during the day. And once that heat is captured inside of a structure, it's going to slowly go away in the overnight hours. Passive solar systems allow the house to act as a solar collector. And systems that passively heat in the winter frequently passively cool in the summer. The large plantations that were built all across the southern portion of the east coast of the United States had the large windows and lots of doors around them. In the winter, that would trap sunlight, and the sun would attract sunlight and would trap the heat inside the glass panes. During the summer, they would open them to allow for more breezes, so that worked as opposed to needing heating and cooling systems. We can also use active solar heating, where a fluid of some sort, water, antifreeze are frequently used, captures the heat and sends it to a tank that absorbs heat. Usually a tank of gravel or of water or of clay. So you're capturing the heat, sending it there, and then transferring the heat to another medium. And then that will be used to heat something else. So you're capturing the heat, redirecting it elsewhere to actively heat something else. In China, this is used in about 10% of their homes to heat water. So as opposed to using electricity to heat your water, you use an active solar heating system, usually with gravel and clay beds. You can get them in the United States to do this.
About how efficient are those?
Well, considering the only energy that they're really wasting is energy that would have been heat already, I don't know if I'm sure there's someone's I don't know. I haven't seen any calculations because everybody just assumes that it's energy that would have been wasted already, so it doesn't matter because any energy used is energy that would have otherwise been lost.
Expensive.
That's where your expense comes in, is the installation cost. But over time, you save a lot of money in the long run. So there's money you have to put in originally. However, if you wouldn't have heated your water prior to that, any cost is better. My advisor in grad school had an active solar heating system for his water heater installed. I think it was a couple $1,000s. And his is connected to solar panels. But for a couple $1,000s, he never has to pay a single bill ever again for his water heater. So in a few years, he'll make all of the money back. A solar thermal system relates to this idea of using, capturing that solar energy and transferring it to heat energy. And you then boil water with it, which creates steam, which turns turbines. Photovoltaic cells are what you tend to think of as solar energy. These are the solar cells that you put on the top of your house. These are the second fastest growing energy source currently in the world. They're considered entirely after the structures have been made clean energy. Making photovoltaic cells takes a lot of energy, and we're working on creating them to be better, faster, and cheaper to make. At one point in time, making photovoltaic cells required the use of hydrofluoric acid. For those of you that have taken a lot of chemistry or any chemistry or watched like enough Grey's Anatomy episodes, you know that's a really bad acid to play around with. I have a friend who quit grad school working on solar cells because he was told he was going to spend the next 5 years working with hydrofluoric acid. He said no. We're now up to the third generation cells that require none of that. So we have made massive strides, and the current ones they're working on will be flexible and you can roll them out onto surfaces. But energy storage is bad. How do you store this? You have to have a battery that it attaches to. If you can utilize the energy right away, it's easy. But then how do you store it? And what do you do at night? You have to have stored energy so that you can utilize it. Have any of you seen these before? Solar ovens and solar cooking surfaces using mirrors to angle the heat so that it cooks your food for you. These require no energy whatsoever. We're using these all over the world. We're not using them in the US, but you can purchase them here, especially if you do a lot of camping and you want to have another way to cook food, or if you're into like a tiny house and you still want to have an oven. Solar oven is the way to go. This is the concept of passive heating, that you're using the sun in order to heat the entire home. When you do it, you will have different sizes of windows and different walls to trap more sunlight. You will also tend to find areas that will need to have ventilation to help the heat move through the house so that it doesn't get trapped in one place or another. This one is the active solar heating, where you are heating your water tank with solar energy. These are solar cells, but if you notice, they are curved. Why do you think they might be curved?
Maybe so that as the sun moves, it's still.
These actually have tracking systems built into them so that as the sun moves, the whole system will realign with it. The curvature concentrates the solar energy even better than it would if they were a flat surface. So they're curved to concentrate it, and they have a tracking system in order to go with the sun. And they can also change the tilt of these for seasons. So our new solar energy, they're called solar farms, are actually really, really high tech. How's that? So our options are this, not this. First choice.
Yeah.
I also like the full darkness.
I would appreciate the full darkness, but some of you want to stay awake and take notes. So some light is better than all dark, I think. Okay, so hydropower it is. How do you think hydropower relates to solar, wind, and geothermal as for its usage as a power source right now? What do you think we use the most of our alternative energy sources?
I think solar, because hydropower seems like only these people who live on like the coast of an ocean would be able to use it.
So Liz thinks it's solar because location dependent. Hydropower is location dependent. Anybody else have another opinion?
Can't hydropower be not just from the ocean, like
Mhm.
movement of any water? So I don't know how much we use it though.
So deserts wouldn't be able to use it.
Deserts will not be able to use it, correct. How do you say it is solar?
Is it solar versus hydropower?
Solar versus hydro versus wind versus geothermal.
Doesn't the US use so much wind?
Believe it or not, hydro is actually where we get most of our electricity from the renewables. Maybe not in the US, but worldwide hydro is used a lot. Hydropower has been something that's been contentious in a few situations. We'll mention that probably later. China had some pretty contentious situations with hydropower at one point in time. They flooded an area that they constructed a dam for hydropower for and displaced well into the upper thousands, if not millions of people, because they flooded an entire valley. Mostly, we will use hydropower where we have an area already where there is a dam that's built and a reservoir behind it for storage of water. And we use then the power of the water flowing over the dam in order to turn turbines. The turning of the turbines is then generated into electricity. Hydropower is something we've been using for quite some time. It was used almost exclusively in the 1800s in a lot of the mills for the grinding of flour products. If they didn't use windmills, then they used water in order to turn the large water wheels to generate electricity for the movement and creation of mill products. It's considered to be relatively inexpensive once everything has been constructed. Water is seen as being pollution-free because you're not adding anything to the water, you're not really taking anything from it, and it is seen as a renewable source. But it's only about 13% of the potential has been developed because it does have environmental impacts. You have to build the dams in order to use water as a power source. So you have to destroy other land areas. You have to construct a dam in a river or in a large body of water, which is then going to disrupt the flow of water and the movement of fish and other organisms. It can flood the land behind where the dam is constructed, and it can cause sedimentation problems. Frequently, in areas where there are reservoirs, you need to dredge out the sediment from the bottom that accumulates there, because as water slows down in its speed, it's going to drop out any of the soil or sand or sediment that it's moving. So you get a lot of sedimentation behind a dam. About 17% of the areas worldwide where hydropower could be used, it's been started to be used, which means there's a lot of areas where we could use hydropower. But most of the areas that are going to be good for hydro work are in remote areas where there's not necessarily a lot of people. So continuing to expand hydropower is going to be difficult. China is expected to double its capacity of water power use by 2020 compared to what it had in the early 2000s. However, the United States is about at our capacity for use of hydropower. We don't have that many large rivers left in order to build a dam and use a reservoir on in order to create hydropower. So that is going to be a problem for us moving forward. There are systems that are called micro hydropower systems that are smaller, and they're expected to have fewer impacts, but they're also going to generate far less electricity because they are going to be on smaller bodies of water. Tidal systems and wave systems have also been developed. In tidal systems, the idea is that the tide will generate water as it moves across it as the tide flows in, and also it will generate movement as it flows out. So there will be, the turbines will be rocking back and forth with the tide. Wave motion kind of works the same way. There's a problem with this though. These systems are probably going to be very hard to build and expensive to build. Additionally, you're going to use very different construction to get the electricity back to shore because you have to get it back to shore. Where we build on a river, it's usually that our electrical generating plant is right next to it. With this, it's going to, the electrical generating plant that connects to the electricity grid is going to be inland. So you're going to need wires that are going to take it from the coast inland. Additionally, you can't have it right at the beach because who wants to go to the beach and just see power generation systems as opposed to areas where you can actually go in the water? It has to be deep enough that it doesn't interfere with shipping channels. So at one point in time, we thought tidal and wave generation were the way to go. There are a lot of problems, we think, with actually implementing it. This is a picture of a dam, obviously, but which one? Actually, I don't know which one. Our next type of power is wind power. Wind, I mentioned last time, is going to work by the use really of solar energy because the changes in solar radiation and how sunlight hits the earth is going to determine how winds are going to move. It deals with the movement of air by solar heating. It is an indirect form of solar energy, and it is a very different type of energy creation. But there are some problems with wind power. We've been using wind generation for a long time. It works. The wind turns the turbines, the blades move, creates momentum, creates movement, and that is trapped, converted into electricity, and then sent to people nearby. We've used windmills at mills forever, since we thought of it as an idea. In the 1930s, the use of windmills in the United States declined dramatically. Anyone want to guess why? Expansion of fossil fuel use and the building of a larger electrical grid that allowed rural electrical lines to provide people in areas with electricity from the burning of fossil fuels. And now we're asking them to switch back. In the 1970s, wind farms started coming back as a concept. It is currently the fastest growing alternative energy or renewable energy source in the world. We expect it has the potential to provide 30% of the electrical needs of the entire world. And in some areas, there's enough wind to be able to provide everybody with all of the energy that they're going to need in that area. It's a clean, renewable energy. The only cost is making your windmills and installing them. But aesthetics are an issue. People object to having to see the turbines. They're ugly. They're large. I bought this beautiful house on the coast. Why should I have to look at it instead of seeing the ocean? I see the ocean and some turbines. I don't want that.
Can't people just color them and pretend they're pinwheels?
I like that as an idea. It would work. How many of you think it's a ridiculous thing to say they're ugly, so we shouldn't use them? In some communities, that has been the objection, especially if the people have a lot of money. This has come up in areas off the coast of Martha's Vineyard, Nantucket, so the islands in New England. People have spent tens of millions of dollars on their properties. They don't want to see what they don't want to see. One of the things that we are doing is looking at whether or not we should move things further offshore and how far offshore could it go. New Jersey and Delaware have both at different times looked into installing wind farms offshore. These are not expected to be as big of a problem for ship navigation as the wave generation because you're going to have them in a group and you can group them in certain areas. And then you can know where they are and ships can go around them. Another thing that has been an objection from people about wind power in the past is that it's going to disrupt the bottom of the ocean floor communities. But we're finding that offshore, it provides like an additional location for the organisms to colonize. So you can actually find greater diversity of organisms where you have this because there's another surface for them to live upon. And wind farms may very well be a tool of the future. We are finding that farmers might be interested in not only growing crops, but in having solar farms or wind farms on their property as well, because you could put the solar panels and the windmills in areas where you can't necessarily grow crops, which would give them another source of potential. This is showing us where wind power could be possible. We're in one of the good places for wind power here. There are some places where wind is not necessarily going to be able to provide a ton of wind, but if you also look at Africa, India, they could produce a considerable amount of electricity via wind power. Maybe this won't work as well in the northern reaches of North America or in Europe and Asia, but it can work elsewhere. There are some drawbacks to these alternative energy sources. We've kind of mentioned some of these already. With direct solar, it's a medium energy yield. It doesn't give us as much energy as we would like. It's economical for heating, but maybe not for everything else. And you can't use direct solar everywhere. But if you design your house in the correct way, direct solar works. Solar cells are costly. They're expensive. We're working on bringing the price down. They're becoming cheaper as we figure out how to build them better and start to mass produce them. That is helping with the price. Tax breaks and incentives and the concept of being able to sell electricity back to your electricity supplier are also going to help with the cost problems with solar cells. They have historically had a low net energy yield, but the newer generation ones are getting a higher net yield than they used to get, so they are improving with that. But you still have to deal with inconsistent sunlight, battery storage, and having a backup generator.
How long do they last when you get them installed, like before it breaks down? Because I've heard people say that like disposing of them after they break down is really a problem, but I don't know.
Some of the companies now you don't actually necessarily buy them and own them outright yourself. You rent them from the company, or it is some sort of a cooperative thing where the company still owns them, and you pay them back a percentage of the cost. With those companies, if it breaks, they will come replace it, and they will incur the cost, so you don't incur it as a person, and they have the ability to better safely dispose of it. Mm-hmm. I think some of them were rated to last on the 20 to 30 year timeline. What they're trying to create are solar, especially the ones that will be able to roll out, that'll be able to roll flat on a roof. They're trying to be able to create them that have a lifetime of at least 50 to 100 years so that it would last the same amount as your roof. Or, well, at that point in time, much longer than a roof, because most roofs last 15 to 30 years, depending upon what they're made of. The concept is to be able to get them to last longer than a roof, so that, and basically to last our lifetime, or your lifetime from the time you own the house. We're not there yet. Breaking of them can be an issue in some areas, especially if you have a lot of hail and other things, and there's a lot of destruction. But they are really strong, because things like your car doesn't, a piece of hail has to hit the right spot to break your windshield. And it's similar with these. Trying to think. I haven't known anybody. I know people that have them, and I haven't known anybody that has had a problem with breakage or with disposal yet. But everybody that I know has had them for fewer than 15 years. Wind, tons of advantages, right? High energy yield. We can do a lot with it. We haven't done it everywhere we could. Maybe people think it's ugly. Maybe they don't like the transmission lines. Along with them looking ugly, some people don't like the noise. And have you ever been near a wind turbine? Is it loud? It's definitely quieter than fireworks. Much quieter than my neighbors celebrating the Eagles Super Bowl win. I don't find them to be that loud. Is there a noise? It's kind of a constant background noise, but in your house, you won't hear it. I personally find like the bug zapper light buzzing noise to be a little bit more annoying than I find this. So for me, that's not a concern.
Is that only when they're turned on? Or is that constant because of the generator?
They aren't really. What do you mean by turned on?
Like I've driven past like big fields of them, like out west, and like a quarter of them will be just like turned off, like they won't be spinning.
There may not be the wind then.
Well, then the ones beside it are spinning.
It depends on the area.
Yeah, I don't know if it was just maintenance.
It could be maintenance.
Or-
I don't know.
It was like a lot of it would be maintenance, but I don't know. And it wasn't like in a row. It would be like every 5 or 6. Like,
Well, and
it'd be all-
I don't.
yeah, I don't know. I've always like wondered about it, but I didn't know.
Sometimes it is maintenance. Other times there may not be enough wind for everything,
Okay.
so they may not. But there's really the ones that I'm used to that you don't really turn them off.
Okay.
Because when the wind picks up, they start moving
Right.
more. If they're the areas where they are turned off, I don't know. All the ones that I've been in haven't had that
Okay.
problem. But there could also be something, and some of them now they're trying to develop that don't have the same number of blades. They're trying to go from, some of them have 3, some have 4, some have 2. Some of them they're working on developing some with 1 blade where it's able to potentially catch more air and by changing the shape of the blades. So they could have been doing maintenance work on them when you drove by, potentially.
Yeah.
The noise is going to be associated with the movement. There is going to be some noise from the movement of the blades and also from potentially the transmission of power. But it's not anything like your fan. If you have a fan on in your room, the blades moving produce a little bit of noise. Is it obnoxious noise? Only if it's really hot and you've got the fan on like as high as possible, maybe. So think of it as a fan type of noise. Here's perhaps a bigger drawback for all of you. 40 to 100,000, somewhere between 40 and 100,000. 40,000 and 100,000. Birds and bats die every year from collisions with wind power. What do we think about that? Is that an acceptable loss?
It's usually a lot of like important bird species too, isn't it? Like birds of prey and stuff.
Some, I wouldn't say a lot of. There's some percentage of them. A few years ago they looked and it was something like 6 eagles.
Okay.
So it's some. It's not necessarily a high percentage. In some areas it may be a higher percentage. Usually it's some of your smaller birds.
They're not clear like windows. What's causing
They are
them to-
not clear like windows. That's true.
What's causing them to run into them? It's not like
They
can
move
see it.
though.
Yeah.
So it's spinning. And they may not see it as much. So it may look a little clearer. Also, if they're in areas next to farm fields and the birds are there eating and they aren't paying attention as they're landing and taking off, especially in a large group, it becomes problematic. We've developed new technologies for this. Think of them as streamers, because for the most part, some of them are literally streamers that we attach to the blades so that there is stripes of color moving, because a lot of windmills are made white. If you're a bird, what color are the clouds? White. Are you afraid of flying into things that are white? Not usually, because you don't hit them. So if we can have something that breaks up the shape of them, either brightly colored or metallic and shiny, it allows the birds in order to see them better, and it causes less problems. One of the other things happens at night, because bats are clearly out at night. They may not be able to see them at night, and their sonar capabilities and their echolocation won't be able to notice them because these blades are in movement. And that movement can also influence where they think things are. So for bats, it may be more of a problem. In some places, they're working on using some infrasounds or other things in order to generate a noise that will keep bats away from them, as a way of still being able to utilize them in an area where there's large groups of bats. Would this work, do you think? Could be a little bit more expensive. But do we always have strong winds? Sometimes you have days with no wind at all. So you're still going to need a backup energy source even with this. Hydropower, it's renewable in the sense that we are always going to have water, but as sediment builds up behind your dams, you're going to have to clean them out. So it's not like you can build a structure and have no maintenance over the long time. We can't use it everywhere. It floods areas. It creates movement problems for fish species. We're close to. So biomass is another type of renewable source of energy. It's a pretty ancient use of energy. The concept is that we can burn wood or other types of biologically produced media, create heat, utilize that heat for cooking or for other purposes. Biomass is, in this perspective, anything which has derived the energy from photosynthesis, either directly or indirectly. In some of the poorer countries, 95% of their energy is created through the burning of biomass. That might mean either a campfire to cook upon or burning biomass in order to create steam to move turbines. So using biomass potentially instead of coal or natural gas. Wood is the largest form of biomass that we use. However, we have started going into different forms of biomass because we're using biofuels, biodiesel, and ethanol. Ethanol is not the silver bullet we were sold originally, the concept that this will be able to get us to transition from oil to a plant-based structure. It's not really working. Ethanol is more expensive to produce from corn than it is to produce corn to feed people. And that's a problem because you're taking away something that could be feeding people and making it something that runs their cars. So you might be solving one problem, but you're creating another problem. It's driving up the cost of corn products, and it does rely on government subsidies. Do you know that you can buy a kit online to make diesel engines run on French fry oil from McDonald's? Or you can retrofit your car to run on frying oil? That might be a slightly different thing. However, then you're left with one other very large problem. Your car smells like French fry oil. For some of you, you're like, no big deal. There's some drawbacks to biomass as an energy source. It's renewable only when your source grows back. And in some areas of the world, firewood shortage does become a problem. And population growth makes this renewable concept a little bit uncertain. There's also the potential for soil depletion and land degradation as we grow firewood. Having said that, about 3 billion people worldwide rely on wood, on charcoal, on dried manure, or other types of biomass as their fuel. So this is used everywhere. Biomass plantations are problematic, where we just cut everything down and we grow the trees that we need for biomass production. It doesn't work well because it does destroy the land surface. And sometimes it's not really energy positive. I mentioned that ethanol from corn doesn't necessarily produce the energy we expect it to.
Does burning things cause pollution? Or?
Does burning things cause pollution? Yes, it would, right? And you've all heard about air pollution before. And you've all heard that it's mainly outside, haven't you? Indoor air pollution is actually a massive problem. And for the developing world where they use biofuels as a fuel source, indoor air pollution kills lots of people from the cooking fires being indoor. Because all of the smoke, especially as things don't burn completely, it does create more pollution. How many of you like being outside around a campfire? How many of you would like it if the campfire was in your house with you? And you had a chimney, you're okay, right?
Yeah.
What if you don't have a chimney? And your house is filled with all of the smoke, and that's where the problem comes from. So there is human effects with air pollution, with all of the smoke constantly being breathed in, but it does produce carbon dioxide. Carbon dioxide is stored in plant material through photosynthesis. So when you are burning it, you are releasing that stored carbon dioxide.
So is it less, like, is it just less used than fossil fuels, so it's not as big of a problem, like, in terms of contributing to climate change? Or
Probably yes. Having said that, when we look at deforestation practices with slash and burn and things like that, it actually has a massive effect. So if you are doing areas where you are having wood and you're collecting especially dead wood or down wood, and you're not cutting down all the trees in an area to create wood, then it's not as much of a problem. Or if you are sustainably removing trees and allowing others to keep growing, then it's not as much of a problem, because there are still standing trees in order to keep storing carbon dioxide. But with slash and burn work, where we go in and we cut down all the trees and we burn everything up, it is seen as a problem. Does that make sense?
Yeah.
But indoor air pollution wise, biofuel burning to create heat and to cook things is actually a massive concern for human health. And okay, what is one thing? Let's imagine you are burning dried manure. Could that potentially also release pathogens? If it doesn't burn hot enough, it absolutely can. Because you have to burn it hot enough in order to kill all of the pathogens for it not to release pathogens. Anyone want to drive your car on sugarcane fuel instead of corn? Sugarcane yields more energy than corn. And you can actually get it from not just the part that causes sugar that we use to create sugar that we use, but you can get it from other portions of the plant in order to create a sugar-based ethanol-like fuel. So materials that would otherwise go to waste we could use. It's expensive. You have to get people to work with it. Brazil uses sugarcane byproduct often, and it has a much higher energy yield than the corn-based ethanol. There is the conception or the concept that we can use cellulosic ethanol, which is creating ethanol from the parts of plants that we don't use for anything, but we haven't gotten there yet. There is another concern with using food sources for energy. You raise the food price. When we divert food into energy, we reduce the amount of food available, and we do raise the price of food, which creates more problems for people in poverty. There's another type of biomass that we're considering using as an energy source, but we don't have it working yet. Algae. If we can genetically modify algae to create ethanol products, it would work. It would be cheap. It would be easy. It would divert nothing from the food supply. And algae can actually remove high levels of nitrogen from water. They can reduce carbon dioxide in an area. So maybe they could actually clean the water, take in carbon dioxide, and create fuel for us at the same exact time. That sounds awesome, doesn't it? We're just not there yet.
And it would have to be genetically modified to be able to do that.
Not necessarily. The concept is if we genetically modify it, it'll work a lot better. But there are people working on how can we utilize products that algae already make in order to create a fuel. Because some of them do have oil-like products in their bodies and lipid products. So maybe we could use. Let's see. Geothermal energy is energy stored beneath the Earth's surface. This has potential in some areas. It comes from the natural radioactive decay of the Earth's crust. The Earth has a molten interior. It's going to continue to be radioactive. It's going to continue to decay and produce heat as a byproduct. Sounds great. The heat comes up to the Earth's surface. We usually see this at geysers or at hot springs, where it cracks out from the Earth's surface. But the ground is warmer. If we can tap into the ground, we can tap into the geothermal heat pump system. We can utilize the heat there to at least heat our buildings, but also maybe we can utilize that heat to create energy. This will not work everywhere. It can't possibly work everywhere. If you find a place where it does work, you can utilize it. You build the system, and it provides you with clean and cheap energy after you've installed your system. But you can't really transport that heat energy anywhere. So it's not transportable. Any of you been in a building with geothermal heat before? Any of you have heat pumps at home that run the heat for your house? Heat pumps tend to be noisy. Geothermal heat pumps are very noisy. I worked at Stroudwater Research Center, which is in Chester County, when I was a postdoc, and they have a geothermal heat pump system. It's noisy. Did it work? Sure. There was also uneven heating of the building, which was only partially related to that. But it was a very noisy system, and it happened to be outside of the lab I worked in, so it was remarkably noisy. If these are not built correctly, these systems can release the gases that are below the Earth's surface, which may contain health hazards. But if we can do that, it's energy efficient. As long as we get it set up right, it's environmentally clean, it's reliable. The concern is how deep can we go with these systems, because it costs a lot to drill down into the Earth's surface. We're hoping that the technology will change, where we can find areas where we can actually drill into an area, pump water down so we don't have to bring the heat up through the gas. We can pump water down to grab the heat and then circulate that warm water through an area, allowing a combination of geothermal with hydrothermal heating. Could work well. Right now, Iceland is using geothermal to provide 3/4 of their energy. California uses it to provide 6% of their energy. But Iceland is more tectonically active and has more geothermal heat coming to it than California does.
I'm curious if there's any sort of like concerns or research that's been done with what the implications are of removing the heat like from below the Earth. Because I mean, it seems really ideal because like it's there, but also I mean I feel like it's there for a reason, and if like removing it, I don't know if that like disrupts like a balance or something.
We don't think it does because in a lot of areas it already does come up through hot springs and geysers and through other things. So it's the idea that there is a slight concern of what would that do if we had a lot of geothermal in a large area. Would that decrease everybody's availability to use it? But we don't think that it will disrupt the Earth's internal system because we're not actually able to go down very deep. If anything, it could decrease geysers and hot springs, which if you owned a hot spring where people came for relaxation and rejuvenation would make you very upset. But we don't think it has any long-term Earth effects. However, the idea of drilling down and pumping water down could. We haven't looked at that yet, in part because the technology is just not there. You can use geothermal for both heating and cooling because the Earth's surface at a certain depth is about the same temperature year-round. In the summer, the Earth's surface is cooler when you go down. Actually, how many of you have ever planted a plant in the summer and felt that as you dig down even about like 6 inches into the soil is way cooler than the ground than it is at the top? It's true, you know this. And if you were to break through the top portion of the ground surface right now that's frozen, you would discover that it's warmer that same 6 inches down. So if you can tap into that year-round, maybe it won't be able to heat and cool your house entirely, but it can decrease your heating and cooling costs if you're utilizing the temperature difference that is already right there next to your house. Do any of you have a basement? Does your basement, is it heated and cooled? So it gets probably a little warm in the summer, a little cold in the winter, but it doesn't change near as dramatically as the rest of your house temperature does it? Cody.
How, generally speaking, how far down do these like pumps and stuff have to go into the ground? For like a home, I guess.
I don't know. I'm going to assume 20 to 50 feet because you're going to want it beneath your basement. and it's going to be beneath the foundation of the structure of the home. I know that in this area, we get around 6 inches deep is where we start to get the area where it is about the same temperature year round. You just need to get through the first 6 inches of the soil. So that really doesn't help. I just remember that from ecology when I was an undergrad, that she had us tested by putting soil probes out at different depths and leaving them out for the entire semester to see how we saw the change in temperature. And we were shocked that it was 6 inches. It was in Lancaster County. I can't imagine it's that different here. But you would want to sink it underneath your system. Alternatively, you could install it as you put an addition on, where you can see in these pictures here, part of the system is further away from the building. And then you would not need to go as deep next to your building or underneath your building. You can see the hot springs there. Have any of you traveled to hot springs before? What was it like? Nice? Very nice. I visited this one is a picture of one in Iceland that actually they're using the same geothermal energy there for the hot spring as they are to generate electricity. I was in a hot spring in Israel and we were shocked by how hot the water was coming out of it. Like there were areas that were just too hot to go into.
Yeah. I went in New Zealand and there were like different pools that had different temperatures. But then also there was this one town that had a ton of hot springs and smelled like sulfur.
They will.
The entire town smelled like sulfur.
Yes.
I don't know if that's all areas where there's geothermal.
Not all of them are going to smell that strongly of sulfur, but it deals with what bacteria you have there. And the first of the anoxic, so the bacteria that don't use oxygen that you're going to get are going to be your sulfate reducers. So they are going to create elemental sulfur as a byproduct, which will increase the smell of rotten egg. It's the same smell that you get in salt marshes, but very strong.
Yeah.
Because the heat is going to help dissipate it really nicely. This is a greenhouse in Alaska that uses geothermal to heat the building. And then we have the hope that everybody has, right? Hydrogen. Hydrogen is going to be our savior for electricity and cars. Except it doesn't work so far. Hydrogen is abundant. Not in a useful form for energy creation. But there's lots of hydrogen. It's basically free. And as we utilize hydrogen, it's going to be clean, even in its final form. Because what are we going to do with hydrogen? Does anyone know? We're going to combust it. Just like we do natural gas. When you combust natural gas, it gives off carbon dioxide. The idea here is that you're going to combust hydrogen. You're going to need oxygen to do it. And as you burn hydrogen, your waste product is water vapor. How does that sound? Anyone think it sounds too good to be true? So far it is. Because, well, first you've got to convert it into a usable form of hydrogen. You've got to make hydrogen gas. And then you have to transport it and store it and all sorts of things. Because hydrogen in our world is not usually found as H2 gas. The current technologies are really inefficient. They cost more in electricity than they produce. We're not going to do it if they cost more than they produce. You cannot use energy that as an energy source that requires more energy to produce it. That's just never going to fly. No one's going to let you do that because it provides a negative net energy yield. We expect if we can make hydrogen fuel cells that have hydrogen in them that will work, that this will allow us to replace oil as a fuel source. There are some drawbacks to geothermal and hydrogen energy. The cost, the amount of land for geothermal becomes problematic. there is the concept that we will be able to deplete the resource. We don't know what that will look like. No one has done enough work with it yet to have an idea of what will depletion look like, and will it have an impact on us. We do know that, let's say Andrew has a house with geothermal, and then Kaylee has a house with geothermal, but then everybody else in the same area decides to tap into the geothermal, that the output from geothermal energy that Andrew and Kaylee got is going to decrease as the people nearby them utilize it as well. But we don't know what that means worldwide. Hydrogen? It's not working. Use energy to make it. Difficult to really make it work at all. And producing hydrogen gas burns fossil fuels. So we're not going to use that as our way of things forward. For non-renewable energy, oil is your first one. It was discovered in 1859 in Titusville, Pennsylvania. It comes from things that are 100 to 500 million years old, and it's one of the most useful materials we have worldwide. Absolutely. But we've used up our mostly easily accessible oils, and now we're trying to get the deeper oils. We're trying to find other types of oil. Hydraulic fracturing is not going to solve this. Fracking is the other word for that. You've heard of fracking? There's a massive, massive problem with fracking. There are lots of massive problems. One, earthquakes. Fracking causes earthquakes. Two, the fracking companies do not have to tell you, or the EPA, what is in the chemicals that they pump in the ground in order to get the oil out. Three, we have found multiple areas where fracking has contaminated people's groundwater. That's just the start of the fracking problem. The earthquakes are considered by a lot of people to be a big, big problem. For me, it's really the chemical constituents that are going down that we don't know what they are. And if you're on the property where your groundwater becomes contaminated, you are not legally allowed to go after the fracking company for restitution because it's part of the way that they are regulated. You don't get to go after them. Fossil fuel lobby is powerful, people. Sorry to tell you that. The environmental costs of fracking, totally uncertain. The environmental costs of things like tar sand mining, also really expensive. We'll get there. But we use oil for everything. Plastics, paints, pesticides, fabrics, medications. Your car, everything utilizes oil. 34% of the world uses oil for their energy, but 37% of the energy in the United States is from oil. 77% of the proven oil reserves are owned by OPEC, which includes a list of countries like Algeria, Angola, Ecuador, Iran, Iraq, Kuwait, Libya, Nigeria, Saudi Arabia, UAE, and Venezuela, also known as mostly countries we're not on a good relationship with. We only have 2% of the world's proven oil reserves, yet we use the most of it every single year. We expect, your textbook says that we're going to run out of oil between 2018 and 2038.